This is the fourth video in the series dedicated to Bessey Shuffle diagrams. As a reminder, a shuffle S is said to be a Bessey Shuffle if and only if S preserves or inverts Bessey sequences. Recall the Bessey sequences of order 8 are 1, 0, 0, 1, 0, 1, 1, 0, and its inversion 0, 1, 1, 0, 1, 0, 0, 1. To aid us in interpreting these diagrams, I've indicated here that half of the digits between 1 and 8 have been color-coded red and half have been color-coded black. So we have 1, 4, 6, 7, black, and 2, 3, 5, 8, red. Written in set notation, we get the following. Also, as we will see, there are times when the Bessey sequence is preserved exactly, and we'll show you what that means in just a moment, or it will be converted to what we call an inversion of the sequence. Furthermore, let me emphasize that the Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0 satisfies this first set of conditions, namely, the 1s are in positions 1, 4, 6, 7, and the 0s are in positions 2, 3, 5, 8. The inversion of this sequence results in that relationship reversing. Namely, the 1s are now in positions 2, 3, 5, 8, and the 0s are now in positions 1, 4, 6, 7. The next shuffle in our series is the Pharaoh in shuffle. So let me go ahead and show you how this shuffle works for a packet of 8 cards. So I have here a packet of 8 cards labeled 1 through 8. We will now perform the shuffle. So how the Pharaoh in shuffle works is you go ahead and just fan out the cards, and note that this is the top card here, of course. So what we're going to do is grab the bottom half of the packet. Now for a Pharaoh in, what needs to happen is the top card here needs to go underneath the top card on the left. And we'll do that by having the one on the right lower than the one on the left. And then you just perfectly interlace them. That's all we're doing. That's the Pharaoh in shuffle. So let's take a look at the new ordering of the cards. Okay, so the new ordering will be 5, 1, 6, 2, 7, 3, 8, 4. And so that's what I've written for our Cauchy's 2-line notation of this permutation. 5, 1, 6, 2, 7, 3, 8, 4. Now we can convert that to cycle notation as follows. We see that 1 goes to 5, so I have an arrow to 5. Where does 5 go? 5 goes to 7. 7 over here goes to 8. 8 goes to 4. 4 goes to 2. And then 2 wraps around and goes to 1. So that completes that cycle. So we actually get quite a large cycle, a 6th cycle here. Now for the remaining cards, we get the following. 3 goes to 6, and then 6 goes back to 3. So we get a little 2-cycle, or what is also called a transposition. Now if we color code our numerals, we get the following. We'll get, now remember, 1, 4, 6, 7 are color-coded black, and 2, 3, 5, 8 are color-coded red. So we get black 1 gets sent to red 5 gets sent to black 7 gets sent to red 8 gets sent to black 4 gets sent to red 2, and then red 2 gets sent over here to black 1. In a similar fashion for the transposition, red 3 gets sent to black 6, which gets sent back to red 3. So we can see here that each value gets sent to a value of the opposite color. And when that happens, inversion has indeed occurred. So as a reminder, inversion occurs when the cards in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8 in some assignment. And the cards originally in positions 2, 3, 5, 8 get moved to positions 1, 4, 6, 7. So the way that we describe an inversion is as follows. The set A gets sent to its complement. The complement of A gets sent to A. So if we relate this to Bessey sequences and begin with the Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0, this means that once this shuffle is performed, we will get an inversion of this sequence. So why don't we go ahead and quickly demonstrate that. So remember, for the Pharaoh in, you take the bottom half of the packet, and we need to perfectly interlace these so that the top card here goes underneath the top card here. Okay? So the way to do that is to start lower on the right and then just perfectly interlace them. Okay? So we get the following, which should be the inversion of what we started with. Okay? And so now we've gotten the Bessey sequence 0, 1, 1, 0, 1, 0, 0, 1 as anticipated. Okay, so let's quickly look at the graph for the Pharaoh in shuffle over here on the left, and you'll recognize this diagram. In fact, we have seen both the inverse of this diagram and an identical version of this diagram. So why don't we quickly remind you of what those were. So as we can readily interpret right from their graphs, the even up jog in which we stack the left pile on top of the right is actually the inverse to the Pharaoh in shuffle. So it's the exact same diagram except for the fact that the arrows are reversed. So what this means then is if we perform the Pharaoh in shuffle followed by an even up jog for which we stack the left pile on top of the right, it will reset the packet to its original order. And vice versa, if we perform the even up jog with left pile placed on top of the right, followed by the Pharaoh in shuffle, that will also reset the packet to its original order. So these two shuffles are indeed inverses of one another. Now that's not the only shuffle to which the Pharaoh in is related. The Pharaoh in shuffle is actually identical to the RC shuffle, in which we deal out the cards into 4 piles, 1, 2, 3, 4, 1, 2, 3, 4. We build up the piles one level at a time, and then we stack the piles from left to right, and that will give you the exact same permutation. And so that's why the graphs actually agree. The Pharaoh in on the top left side of the screen has a Bessey shuffle diagram identical to this RC shuffle in which we're stacking from left to right. Now for those who are new to this series on Bessey shuffle diagrams, why don't we just quickly explain how our permutation gives rise to this particular diagram. So the way that we read this is we begin at 1, so 1's over here, and it gets sent to 5. We can see that up above here. So 1 goes to 5, 5 goes to 7, so here's 5, we're going to go up to 7. 7 right here goes to 8, well 7 goes up to 8, and 8 gets sent to 4, so 8 gets sent down here to 4, and then 4 gets sent to 2, and finally, the 2 here gets sent to 1 at the beginning of the cycle. And that completes that 6th cycle. And we say that the values 1, 5, 7, 8, 4, 2 are in the same orbit. They simply get permuted or rearranged among themselves. And then we have a remaining 2 cycle, which is also called a transposition. So we need to go down to 3. And then there's an arrow from 3 to 6, but also Since 6 wraps around to 3, there's an arrow from 6 to 3. And so they just switch back and forth every time that shuffle is performed. And as already noted, inversion of our Bessey sequence occurs. Our next shuffle is the Pharaoh out shuffle here, on the top row but on the right side of the displayed diagrams. So as you might guess, this is similar to a Pharaoh in except for one slight modification. Okay, so what we'll do is we'll begin with an ordered packet of cards 1 through 8. And now what we'll do differently is we will take the bottom 4 cards. So we're splitting the packet exactly in half. Now what we need to have happen is we need this card to go underneath the top card here. And we'll do that by having the card on the left below the bottom card on the right. And then you just perfectly interlace them. So that is the Pharaoh out shuffle. And it will give us the following new order. We will get 1, 5, 2, 6, 3, 7, 4, 8. And so that leads to a Cauchy 2-line representation as follows. So the top row is always the starting order of the cards. And now we get 1, 5, 2, 6, 3, 7, 4, 8. And this 2-line notation can be converted into cycle notation as follows. We see that 1 goes to 1, which means 1 is a fixed point. So whatever's placed in position 1 gets returned to position 1. If we follow what happens with 2, 2 goes to 5, 5 goes to 3, and then 3 goes to 2, so it wraps around. So we get a 3 cycle. Similarly, 4 is sent to 6, 6 goes to 7, and then 7 goes back to 4. So we get a second 3 cycle. And finally, 8 is a second fixed point. 8 gets sent to 8. So whatever starts in position 8 is returned to position 8 once the shuffle is completed. Now color-coded, we get the following. 2, 5, 3, all of which are color-coded red. And then 4, 6, 7, all of which are color-coded black. And then we normally don't write single cycles when describing a permutation in cycle notation, as indicated up here. We can drop those as long as we know the size of the set that we're working with. So if we keep in mind that the original set was of 8 objects, we can actually drop these. Now I included them just because of the color coding. So we see that black 1 goes to black 1, and we see that red 8 goes to red 8. So what this means then is all of the cards in the red value positions will stay within those positions in some order, and all of the cards in the black value positions will stay in that same group of position values. So what this will mean in particular is that each value gets sent to a value of the same color, and this means that inversion has not occurred. So this simply means that the cards in these positions will stay in those positions, 1, 4, 6, 7, and the same thing is true for the complement of A. Cards in these positions here will stay in positions 2, 3, 5, 8. Now they'll be moved around among themselves with 2 exceptions. Whatever's in position 1 stays there, and whatever's in position 8 stays there. All of the others are actually being permuted. So applying all of this to the Bessey sequence 1001, 0110 means that if we perform this shuffle, it will preserve that sequence form. So why don't we just quickly show that. So here we're performing a Pharaoh out again. So we're going to take the bottom half. So we interlace them perfectly in such a way that the top card on the left goes underneath the top card on the right. So that is a Pharaoh in. And what will happen is it will preserve that form. So we'll still get 1, 0, 0, 1, 0, 1, 1, 0, despite the fact that the ones are moving around among themselves, with the exception of the first one, since that's a fixed point, and the zeros are moving around among themselves with the exception of the last zero, which is a fixed point as well. And let's go ahead and just show you how the Bessey Shuffle diagram was constructed. So if we use the information in our cycle notation of the permutation, we see that 2 goes to 5, 5 goes to 3, and then 3 goes to 2. So let's go down to the graph here. So 2's over here. So 2 is sent down here to 5. 5 is sent back up to 3. And then 3 is sent straight up to 2. And that completes that 3 cycle. So we say that the values 2, 3, 5 are in the same orbit. In a similar fashion, if we begin at 4, so we're looking at the second 3 cycle right here. So it's 4, 6, 7. So 4 gets sent up here to 6. 6 goes to 7, so straight up. And then 7 goes back to 4. So that is the second 3 cycle, for which we also say that the values 4, 6, 7 are members of the same orbit. And finally, we have these 2 fixed points. 8, whatever's in position 8, is returned to position 8. So it doesn't go anywhere in the end. The same thing for position 1. Whatever starts there will end there. Now I've indicated down below that this shuffle is the inverse of shuffle 10. And shuffle 10 is one that we've seen already. So recall that shuffle 10 is an even up jog for which the right pile is stacked on top of the left. And the way that we can tell that this is the inverse of the faro out is the diagrams are identical except for the fact that the direction of the arrows is reversed. This of course means that if you perform the faro out followed by an even up jog for which the right pile is stacked on top of the left, it will return that packet of cards to its original order. The same thing is true for performing the even up jog first with right on left, followed by the faro out. It will reset the packet to its original order. And the faro out is identical to shuffle 44, which is coming up later in the series. Our third shuffle for today is the Klondike Shuffle. So let me show you how that shuffle is performed. So this is shuffle number 15. So if we begin with our ordered packet 1 through 8, we perform the Klondike Shuffle and then we record the new ordering of the cards. So the way that the Klondike Shuffle works is you take the bottom card, just one, and the top card, just one, off as a pair. Okay, and you just set that down. So bottom and top together as one, bottom and top together as one, and then we only have 2 left. Set those on top. So what is the new ordering after the Klondike Shuffle has been performed? Well, it's as follows. It's 4, 5, 3, 6, 2, 7, 1, 8. So that is why when we write out the Cauchy 2-line notation for this permutation, we get the following: 4, 5, 3, 6, 2, 7, 1, 8. We can convert that to cycle notation as follows. So here we see that 1 is sent to 4. So 1 goes to 4. 4 is sent to 6. So 4 goes to 6. 6 goes to 7. So we have an arrow from 6 to 7. And then 7 goes to 1, which wraps around. So that completes that 4 cycle. We also get a transposition, since 2 goes to 5, so 2 goes to 5, and then 5 goes back to 2, so it wraps around. So we get this 2 cycle, also called a transposition. And I apologize, for some reason I originally left off what happens to 3 and 8. So 3 is a fixed point, 3 goes to 3, and 8 is also a fixed point. What starts in those 2 positions will be returned to those positions. Okay, so we do get 2 single cycles here. Now if we color code our cycle notation of the permutation, we get the following. So we get 1, 4, 6, 7. Now remember, all of those are color-coded black. And then we get transposition 2, 5. And those values are color-coded red. And we also get these 2 single cycles, which ordinarily are not included in the cycle notation of a permutation, as long as you're clear on how many elements there are in the set that you're working with. Okay, so we can readily see what's happening here is that each value gets sent to a value of the same color. So in other words, inversion does not occur here. So what it means then is the cards in positions 1, 4, 6, 7 stay somewhere within those positions after the Klondike Shuffle is performed. And cards originally in positions 2, 3, 5, 8 stay somewhere in those positions. And then we have this situation down here where the form of the Bessey sequence is preserved. So no inversion here. In fact, why don't we quickly demonstrate that? So if we begin with the Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0, if we perform this shuffle, we will get back that form. So the Klondike, top and bottom come off as 1, top and bottom come off as 1, top and bottom, and then the last 2 go on top. So what we should get back is 1, 0, 0, 1, 0, 1, 1, 0. And that's exactly what we get back. Now we need to realize that the cards labeled 1 here are moving around among themselves. They really are switching places. And the cards labeled 0s are also moving around themselves with 2 exceptions. The 0 right here in position 3 will stay right there. It will be returned to position 3 after the Klondike Shuffle has been completed. Also, the 0 in position 8 down here will be returned to position 8. And that's because those are fixed points. So if we step through the construction of the Bessey Shuffle diagram, for the Klondike Shuffle, we get the following. So recall, 1 goes to 4, 4 goes to 6, 6 goes to 7, and then 7 goes to 1. We'll just check that. So we have 1 here. It goes down to 4. So we have an arrow from 1 to 4. And then 4 goes up to 6. And then 6 is sent to 7. So it goes straight up. And then 7 is sent back to 1. So that completes that cycle. So we would say that the values 1, 4, 6, 7 constitute one of the orbits for this shuffle. So those values just get moved around among themselves according to the arrows indicated on our Bessey diagram. And then for 2 and 5, which form a transposition, this means that if we start at 2, it's sent down to 5, and then 5 is sent back to 2. So that's why we have a double arrow between 2 and 5. And so since inversion does not occur, that can be summarized as follows right here. And I thought it might be helpful to note that this shuffle here is actually the inverse of one that we've seen, namely Shuffle 12. Now once you know this, you can use this pair of shuffles to ostensibly mix the cards, but in the end, you're leaving the cards exactly where they started. So let me remind you of what Shuffle 12 was. So here is Shuffle 12. It's the Mange Shuffle. In particular, it's the under-over. So what this will mean then, if you perform the Klondike and follow that with the Mange under-over, it will reset the packet to its original order. Or if you originally Mange shuffle the packet of the under-over variety and follow that up with the Klondike, you will also return the packet to its original order. And we can see that they're inverses by the fact that the diagrams for the Klondike and for the Mange under-over are identical. except for the fact that the arrows have been reversed. Okay? Our last shuffle today is the Australian down under. Now, as we'll see, this shuffle is highly chaotic. It is scrambling the cards in a way that none of the other shuffles do, actually. But nonetheless, it will actually be a Bessey shuffle. Now, this one won't preserve a Bessey sequence, but it will invert it, which for our purposes is just fine. Okay, so to show you how we got the cycle notation for the Australian Down Under, we begin with an ordered packet 1 through 8. We perform the shuffle, and then we look at the new ordering. So the Down Under, how this works is you put the top card down, next one goes under, down, under, down, under, down, under, down, under, down, under, down, last one goes on top. So what is the new ordering of the cards? Well, let's take a look. So it looks like it's 8, 4, 6, 2, 7, 5, 3, 1. Okay? And that's what I've indicated down here using Cauchy's 2-line notation. We see that we get the following representation. Of course, the top row is always 1 through 8 for what we're doing. And then the bottom row is 8, 4, 6, 2, 7, 5, 3, 1. Now, 2-line notation can be converted to cycle notation as follows. We look at what happens with 1. 1 gets sent to 8, and then 8 gets sent to 1, so it wraps back around. So we get a transposition, or what's also called a 2-cycle. What happens with 2? 2 gets sent to 4, and then 4 gets sent to 2. We get a second transposition, or 2-cycle. What happens with 3? 3 gets sent to 6, 6 gets sent to 5, 5 gets sent to 7, and then 7 gets sent back to 3, so it wraps around. So we get a 4-cycle. If we color code our numerals, we get the following. Black 1 being sent to red 8, and red 8 goes to black 1, it wraps around. Red 2 goes to black 4, which wraps around to red 2 again. Red 3 goes to black 6, which goes to red 5, which goes to black 7, which goes back to red 3. So we can see here that each value gets sent to a value of the opposite color. And because of that, inversion has indeed occurred. So once again, inversion occurs if the cards originally in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8 in some assignment, and vice versa. Cards that began in 2, 3, 5, 8 positions get moved to positions 1, 4, 6, 7. And in the case of the Australian Down Under, inversion does indeed occur. So using our Bessey sequence 1001, 0110, why don't we go ahead and quickly demonstrate that inversion does occur. So the down under, it's down, and then the next card goes under, down, under, down, under, down, under, down, under, down, under, down. Last one goes on top. So instead of 1001, 0110, we should get the inversion of that, which is 0110, 1001. Okay, so the cards labeled 1 here originally started in the positions currently occupied by the zeros, and vice versa. So it truly is the case that the zeros and ones switch places in some way. That's called an inversion. And to quickly step through the Bessey Shuffle diagram, we can come over here. We see that we have 2 transpositions. So what that means then is we should expect 2 double arrowed lines, one between 1 and 8, which we have right here, and one between 2 and 4, which we have right here. Now the other values are being moved around in kind of a messy fashion here. So 3, so if we go down to 3, which is right here, it gets sent to 6 straight across. So there's an arrow from 3 to 6. 6 goes to 5, which is down here, which you can't see at the moment. And then 5 goes up to 7. And finally, 7 goes back to 3, which completes that cycle. So here we would say that values 1 and 8 are in the same orbit, 2 and 4 are in the same orbit, and 3, 5, 7, 3, 6, 5, 7 are in the same orbit. And here I've indicated that inversion has in fact occurred. And then note down here, I have no indication as to any other shuffle that is either the inverse of the Australian Down Under or identical to it, that I will be featuring in this series devoted to Bessey Shuffle diagrams. Okay, so let's finally show an application of all of this here. Okay, so let's show an application of all of this here. So I have here a bunch of I have here 8 cards. And so what I'm going to do is I'm going to just mix these cards using some of the shuffles using the shuffles that we've shown you today. But before doing that, why don't we just begin to really scramble these cards. We can also perform this first shall be last, last shall be first. This is where I deal down until you tell me to stop. Okay, stop there. Okay, and I'll do one more. And then we just stack in opposite order. So that's called first shall be last, last shall be first. We can do another one of those. Tell me when to stop dealing. Stop there. Okay. Stop there. Stop right there. Okay. And then stop there. Okay. And then we'll stack from right to left. Okay. And now let's go ahead and use our new shuffles in whatever order. And technically, we can use them in any quantity that you would call for. So we could do 5 of one, and then 2 of one another, and 3 of the other, and 7 of the remaining one if we wanted. We'd be here a long time. But maybe we'll just go ahead and perform each of these once. So if you were here, I'd ask you, which one would you like first? You want the ferrule out first? Ferrule out. Okay, so let's remind ourselves how this works. So we just kind of fan out the cards. We take the bottom half of the packet, and then we interlace them perfectly. Now we're going to do it in such a way that the one on the top right will stay on top. Okay, so that will be the ferrule out. Okay, what else would you like to perform? A Klondike next. Okay. Oh, sorry, I didn't even notice I had them face up. Sorry about that. I was looking at my diagram. So Klondike next. Okay, so take the top and bottom cards off as one. Sorry, I'm being kind of sloppy today. Okay, so that's the Klondike. Which one would you like now? A faro in. Okay, let's do that one. So this is where you just fan them out, and you take half the cards, and then we're going to interlace these perfectly is what we're going to do. And so this time what we need is we're going to have the bottom card on the right go underneath the one on the left, and then you just perfectly interlace them. Okay, that's perfect. That's called a faro in shuffle. And then the remaining one that we haven't done yet, I believe, is the Australian down under. So let's do that. So that's down, under, down, under, down, under, down, under, down, under, down, under, down. Last one goes on top. Okay, very good. Okay, so what I'm going to do is I'm going to kind of use my intuition to separate these cards into 2 very special piles. And these are card values that have great significance both in mathematics and in the arts. Okay, so what I'm going to do is I'm going to just kind of deal the cards down using kind of my numerical sensitivity. Okay, let's see, maybe that one there, this one here as well, and then that one there. So hopefully I have 4 in each. Okay, very good. Well, believe it or not, what I hope to accomplish, and so we'll find out if I did, I tried to separate the cards into a pile of Fibonacci value cards. So that would be like an ace, a 2, 3, 5, 8, 13, that kind of thing. and non-Fibonacci card values. So let's see how I did. Did I actually succeed? Well, I don't know, because none of those are Fibonacci values. Those are 1, 2, 3, 5, 8, 13, and so forth. What do I have over here? 8, that's a Fibonacci number. 5 is as well. A king. Is the king a Fibonacci? Oh, wait a second. See, the jack is normally labeled an 11, the queen a 12, and the king a 13. And 13 is indeed a Fibonacci number. So we didn't mess up there. What about the last one? 3 is indeed a Fibonacci number. So somehow, with all of the choices that you made in how we randomized these cards, I was able to nonetheless use my intuition for Fibonacci values to separate those cards without even looking at the faces of the cards into a pile of Fibonacci card values and a pile of non-Fibonacci card values. Wow, how in the world was I able to accomplish that? Okay, so let's show you how that was done. Okay, and you can do this right away. The first thing to do is put out the 4 cards that have Fibonacci value. So a 3, a 13, 5, and 8. The order of these cards doesn't matter. And then the remaining cards will be non-Fibonacci values. Okay? So 4, 12, 11, 10. As you can check, if you're not familiar with Fibonacci numbers, those are not these special numbers that are used in art and architecture and so many found naturally occurring in nature itself. Amazing, amazing numbers. So we have our pile of Fibonacci values and non-Fibonacci values. So that's essentially where I started. I think I started with the Fibonacci values on top is what I did, like that. Okay. Now, what I did first was I performed this triangle deal that we've used a few times in this series. This is a very clever way to convert the packet structure that we just showed you into a Bessey packet structure, so a Bessey sequence now. So you deal clockwise into this triangle, and then you stack in opposite order, picking up the first pile first. So we stack in the counterclockwise direction. Okay, so what that will mean then, let me just show you. These cards will now be in that special arrangement. So let me point that out. So what should be the case, so look at this one. This is a non-Fibonacci value. So if you want to think of non-Fibonacci values as 1s and Fibonacci values as 0s, that would work. So a non-Fibonacci value here, and then we do have 2 Fibonacci values. So this is like having a 1, 0, 0, and then here's a non-Fibonacci value, 1, and then over here we have a Fibonacci value, so it's like a 0, and then we have a couple of non-Fibonacci values, like a couple of 1s, and then we finish with a Fibonacci value 13, which we've denoted as a 0. So this could be thought of as 1, 0, 0, 1, 0, 1, 1, 0. So this is indeed a Bessey sequence. So this special organization is going to be preserved by all 4 of the shuffles today and all of the shuffles that we'll be showing you in this series. Okay. Now I think I also threw in something called the first shall be last and the last shall be first. This is where you just deal out the cards in the piles until the spectator says stop, and then you deal into the next until they tell you to stop, and so forth. And then you just stack in opposite order. So first shall be last and the last shall be first. When we do one more of those, you can do as many of these as you like, by the way. It doesn't matter. Okay, so first shall be last and the last shall be first. So the last card dealt there is the first one to pick up. So you essentially just stack from right to left. Well, each of those first shall be last, last shall be first shuffles is simply a packet reversal. You can check that for yourself. If you start with, let's say, ace through 8, and you perform one of these shuffles that I'm showing you now, it just reverses the packet. So now it'll be 8 through ace. It just reverses the order. So if you do it twice, it brings it back to the original order. But since Bessey sequences are invariants, are not harmed by packet reversal, it doesn't matter if you do this first shall be last, last shall be first, an odd number of times. It doesn't matter if the packet ends up being reversed from what it was before we performed that shuffle. Okay? It won't hurt anything. Okay? Now it will invert the packet, but it won't change anything that we're going to do. It won't undermine anything we hope to accomplish. Okay? And then from there, all I did was I performed these 4 shuffles in whatever order that you like. So I don't know if we need to do those again. So maybe they asked for the Klondike. Okay, Klondike shuffle first. Okay, and then maybe a Pharaoh in next. So this is where you take the bottom half here. Okay, and then you're wanting the one on the right to be lower. And then you just perfectly interlace them is all you do. And then maybe we'll follow that up with the Australian down under. Okay, so this is down, under, down, under, down, under, down, under, down, under, down, under, down. Last one goes on top. And then I think we could finish now, if we want to do one of each, with a Pharaoh out. So you just kind of fan out the cards so you can see them. And you just grab the bottom 4. Okay, just pull those out like that. And then we now want the top card here to stay on top. That's really what we want. So we'll do that by interlacing them in this fashion. Oops, get that to go in. So that's a perfect interlacing. And so we now still have a Bessey sequence. We have something of the form 1 0 0 1 0 1 1 0. Where either the 1s we can think of as the Fibonacci values or the 0s as the Fibonacci values. And then the opposite value will be the non-Fibonacci values. Okay? So if in your mind's eye you can just picture 1 0 0 1 0 1 1 0, that's going to give me the instructions for how to divide these 8 cards into 2 packets, so that we get back to a packet of Fibonacci numbers and one that consists of the non-Fibonacci numbers. Okay, so if you want to think of 1 on the left, so we're going to do like 1 0, kind of 1 on the left, a 0 on the right. Okay, so I'm going to go like 1 0 0 1. Okay, what comes after in the Bessey sequence? 0 1 1 0. Now that's guaranteed to separate the cards into non-Fibonacci values, like those 4, and Fibonacci values, namely these 4. That will work for you every time. Now the amazing thing is we could have not only performed these 4 shuffles that we're showing you today, but you could perform any of the previous 12 shuffles that we've shown you thus far in this series. You can perform any of those in any quantity and in any order before you do this final dealing out. And you'll still finish in the way that we finished here. Absolutely astonishing. So I appreciate you watching, and watch for the next video in this series. It will be the 5th video, I believe, dedicated to Bessey Shuffle diagrams.